Hello students, welcome. Uh, so as you know, in the previous class we studied about linear harmonic oscillator and we defined what is a linear harmonic oscillator. We could derive the differential equation of a linear harmonic oscillator, and we solved that differential equation and we got the expression for the displacement of the body. Displacement of any body which is executing an oscillation with respect to time. So we got x of t, okay, value of x at a different time instant, and we found that it is a sinusoidal one. The solution of the differential equation was a sinusoidal one, or it follow a sine curve or a cos curve. Okay, so using that we can find the position of the particle at any time instant, because x of t is of t, x as a function of t is of t. So position of the particle at any time instant can be obtained. So today we will look into another aspect of harmonic oscillator. That is the energy of the harmonic oscillator. Okay, energy. Because we know an oscillator is oscillating or moving, the body is moving, whatever is oscillating, what is a body of mass, some finite mass. Okay, so that is moving, so it is having some moving energy or kinetic energy. Similarly, it is moving, so it is experiencing a force. That force depends on the compression on the spring. Compression on the spring. Okay. So due to the position of the body also, the oscillator possesses an energy. So by virtue of position at a different dimension, you can see the body is assuming a different position. So it have an energy due to its position that we call as potential energy. Here it is evolved due to the finite pressing, compression on the spring, or elongation of the spring. Okay, anyway, that is attributed to the position. So body possesses kinetic energy and the body possesses potential energy. So we say that a harmonic oscillator possesses two types of energy, kinetic energy and potential energy. And here potential energy is basically due to the displacement of the particle or body with respect to the mean position. So the mean position, you take it as a mean position, how far away or how high heavy. Okay, high means above, below, or how far away, anything. Okay, anything of that kind. So it's basically displacement. So that displacement from the mean position is very important. But this is the mean position in the figure. Okay, so displacement from the mean position is also important in deciding the potential energy. Similarly, for kinetic energy, position of the body. Okay, because at different time instant its position is different, so and accordingly its velocity will be also different. Previous class we have seen that velocity of the particle is not constant. Okay, depending on the position of the body, velocity also varies. So at a different instant, kinetic energy will be different, potential energy will be different. So today we will derive some equation for finding the kinetic energy and potential energy of such a harmonic oscillator. Okay. So first we will look into deriving expression for potential energy of a oscillator. So consider a spring mass system which is moving like this. So every time spring is experiencing a compressive or elongative stress. So there is of course a force in it. So when the oscillator, here the spring, when it is displaced through a distance dx, it will experience a work. Okay, work has to be done because we have to pull up the spring, so some amount of work has to be done. So that work we can find out because here the displacement is dx, so the total work done, that will be dw. Okay, small elementary work done will be equal to force applied multiplied by displacement. Displacement is dx. Okay, so we got the work done on the spring to displace by a small amount dx, that will be f dx. And in case of spring, we know that the restoring force developed inside the spring is proportional to displacement x, or restoring force will be equal to kx. So this small f in the equation we can replace with a kx. Okay, so what we get is the elementary work done dW will be equal to kx dx. Okay, so now the elementary work done become kx dx. Now you can imagine that the body is moved from some e position 0 to some distance x. Then you can find the total work done on the spring or total work done on the body to displace by a distance x. So you can find it. We have the dW here. So you are displacing from some 0 point to some x point, some x distance. So the work done you can find by taking the integral of dW. That will be integral of 0, because it's the initial point, final point is x. So we get integral 0 to x kx dx. And obviously, you know the standard format of integral. K can be taken outside. So integral x dx will be simply x square by 2. Okay, x square by 2. So if you input that, what we get to, you apply the upper limit and the lower limit. What we get is the total work done to displace the spring from mean position to a distance x will be equal to half kx square. Okay, very simple expression we get. So that shows that work done depends on the displacement. Okay, and it vary with the time. Because x will vary with the time. So obviously work done will also vary with time. Or this is stored as potential energy in the spring. Okay, this is stored as potential energy. So we say work done on the oscillator become its potential energy. So whatever work is done, that is stored in the system as its potential energy. So we got the expression for potential energy. Now comes the kinetic part. As far as we know, when the oscillator is oscillating, it is moving with some definite velocity. Obviously, the velocity changes with respect to time. So still we can find the kinetic energy, because kinetic energy expression is given by half mv square. Okay, here velocity part we have derived last time. The last video we can see that velocity was equal to omega 0 into root of a square minus x square. What is say there is a maximum displacement or amplitude, and x is the displacement at any time instant, and omega 0 was the angular frequency of the oscillator. You can substitute this value of velocity in this equation. So we get the kinetic energy is equal to half times mass into v square. Velocity is given omega 0 into v square. So by squaring you can get the kinetic energy. So that happens to be 1 by 2 m omega 0 square a square minus x square. So we got the expression for the kinetic energy, and that also depend on the position, of course, the displacement from the equilibrium position x, obviously. So and that shows that kinetic energy also vary with the position of the oscillator. Okay. So now we have with us both the potential energy expression and the kinetic energy expression. So the total energy of the oscillator can be now found by adding both. So that will be equal to potential energy plus kinetic energy. So we get what? Total energy is equal to half kx square, that is the potential part, and half m omega 0 square a square minus x square. That is the kinetic energy part. Okay, you can add it. So you can separate them. Half kx square is there, half omega 0 square a square is there, and minus half m omega 0 square x square is there. And obviously we know in the last video we have seen that k is equal to m omega 0 square. Obviously, so we can put here. So what happens? Our first term now become 1 by 2 m omega 0 square x square plus half m omega 0 square a square is the amplitude minus half m omega 0 square x square. Okay, the first term and third term you can cancel. So ultimately what is left with us is total energy become half m omega 0 square a square. Okay, here you can see mass is a constant, omega 0 is a constant, and amplitude of oscillation is also a constant. So that means that the total energy of the oscillator is a constant. Okay, even though potential energy and kinetic energy, they vary with respect to time. No doubt they vary. Every instant it is different. But when you add up both the energy, what we get? The total energy of the oscillator becomes a constant. Okay, and you can see that that total energy is proportional to square of the amplitude of displacement of the oscillator. Okay, this is the amplitude, and you can see total energy is proportional to a square. So that is an important result. Okay. Now, in fact, we can plot the energy. We have got both expression for kinetic and potential. You can plot on the x-axis. You take two axes. One is horizontal axis with position and vertical axis with energy. You can plot both kinetic energy and the potential energy on the vertical axis. Okay. So first, you can see take the potential energy part. That was half k square. Okay, if you take x along the horizontal axis and potential energy along the vertical axis, you can see that a half a square will be a parabolic curve. Okay, half k square is a parabolic curve, and this is called the potential energy curve. Potential energy curve. This is symmetric with respect to the energy axis. Why it is symmetric? Because whether x is negative or positive, we are squaring it. So automatically this becomes a positive quantity. So parabolic curve is obtained, and at the mean portion you can see x will be 0, that is here, that means potential energy will be 0, and at the maximum point x will be equal to a for amplitude, then potential energy will be maximum. Okay, so minima comes at the equilibrium point and maxima comes at the peak point, okay, extreme points. And now you go to the kinetic energy part. Kinetic energy was half m omega 0 square a square minus a square. You can take the inverted dotted curve. That is what is showing the kinetic energy part. Okay, and you can see that when you put x is equal to 0 at the mean portion, you will see that energy is maximum. That is what is shown here. This point is the kinetic energy maximum. And when x is equal to a, you can see that kinetic energy minimum. That means at the extreme point, the harmonic oscillator stops. Harmonic oscillator stops at the extreme point, so it don't possess any kinetic energy. That is why energy axis is 0 at both extreme points. So this way you can plot both the kinetic energy and potential energy on an energy curve. Okay, and you can see the middle point here. At the middle point, both kinetic energy and potential energy will be equal. That usually happens at a point that is given as an assignment for you to find out at what point the kinetic energy will become equal to the potential energy. Okay, that we will find out very shortly. And now we have an assignment. Very simple question. At what displacement kinetic energy of an oscillator is equal to 1/4 of the potential energy of the particle executing as a charge? That means you have to find out that point or that value of x at which kinetic energy become 1/4 of the potential energy. A very simple question, because you have the expression for kinetic energy and you have the expression for potential energy. Here the question demands that this condition has to be satisfied. Okay, kinetic energy become 1/4 of the potential energy. You can solve this equation and you get the value of x. Okay, you try to do this problem and do it properly and submit in the Google Classroom. And you have the second problem. At what displacement the kinetic energy of an oscillator becomes equal to the potential energy of the oscillator. Okay, so what question demands that at certain point the kinetic energy and the potential energy become equal. Or you can see the total energy is divided into equal half. First half given to the kinetic part and second half given to the potential part. And the question is asking at what point this will happen. Okay, at what point this will happen. Whenever it happens, this equation should be satisfied. Okay, half of the potential. Okay, so that point can be easily found by solving this equation. You find out that point. Okay, so you can do both questions, I am sure, and submit in the Google class. Hope the idea is clear. We have discussed only the energy concept, potential energy and kinetic energy of an oscillator, and we try to plot them in a graph, and we did some problems. Hope you enjoyed the session. Thank you all of you.